Hello and welcome to this presentation on the roadmap to reliability. My name is Jason Tranter, the founder and managing director of Mobius Institute. In this presentation, I'm going to introduce the benefits of improving reliability and then talk about the roadmap itself and how it deals with each of these issues I've listed. Now, I should say that the roadmap to reliability is a scheme that we've put together, but it's not proprietary. There's nothing in there that necessarily means you have to own one of our products or take our training to learn more about it. It is a holistic view of how you improve reliability, not just the technical aspects, but the human aspects as well. So, very briefly, we have other presentations on this topic. There are a lot of benefits to improving reliability. So rather than focusing on purely cutting costs, if we try to improve reliability, we will reduce the amount of unplanned downtime and we reduce the amount of planned downtime. We reduce our costs in many ways and we reduce the amount of waste that exists. We reduce the number of safety incidents, a reliable plant is a safe plant, and we reduce the number of environmental incidents. And as part of all of this, we therefore increase the availability and we increase the capacity of the plant. We improve product quality and we certainly make the shareholders and regulators more happy with the business and the organization. And finally, and certainly importantly, we help to improve employee satisfaction. Less stress about financial results and downtime, safety issues, the work that's being performed and so on. So, how do we achieve all of this? Well, very briefly, I want to outline that there really are a couple of ways you can go about improving reliability. One of the classical ways is to take somewhat of an analytical approach to it. Collect and analyze a lot of reliability data, collecting mean time between failure, mean time to repair, and that sort of information, and analyze what that data is telling you. And then, and as part of that perhaps, performing classical RCM, which is a terrific strategy, but many organizations as part of their implementation have not been successful. And then as part of that, relying on root cause failure analysis to identify your reliability issues so that you can react to those problems and do something about it, hopefully making changes that avoid those problems in the first place. What we're going to be talking about is something different. We're going to go through a proactive process of addressing all of the common root causes of particularly rotating machinery failure, but also electrical equipment. If you can identify all of the common causes of failure and proactively seek to improve those issues and eliminate those sources of problems, then you're ahead of the curve. You're not waiting for problems and reacting to them, you're avoiding those problems in the first place. It can certainly be justified and has many, many benefits. But in order to make sure our maintenance program is set up correctly, we do need to ask the reliability or the RCM questions, but we're going to do it in a more streamlined way, and I'll outline that in a moment. And we'll still use root cause failure analysis on the exceptions, on those pieces of equipment that do still fail. Even though we've worked on these root causes and we have better maintenance practices, we're still going to use root cause failure analysis. Now, how do we go about doing all of that? Well, it's a combination of physical asset management and people management. So it has to be a combination of what we do with the equipment and that sort of strategy, but also how we work with the people in the plant, from the most senior levels down to the least senior, if I can put it that way. The operators and people working on the shop floor and everyone in between needs to understand what this is all about. And we're going to do that. We are going to use condition monitoring, which is often an approach taken. But we're going to do more than just monitor the equipment and react to the problems that come up. We're going to seek to improve the condition of the equipment we have to maximize the reliability that's possible, and eliminate those sources of poor reliability that come as part of the design and procurement stage. So how are we going to do that? Well, that's what the roadmap to reliability is all about. Now, what I'm going to do here is just build the roadmap briefly, and then we'll go through some detail on each of the areas. So it's very common when seeking to improve reliability that we'll start with some sort of combination of condition-based monitoring, condition monitoring, condition-based maintenance, and preventive maintenance, which I'm going to call interval-based maintenance to make it very clear. So, most people recognize, well, hey, if I use vibration and some other tools to detect problems, I'll get an earlier warning. And that's great. A lot of organizations rely too much on interval-based maintenance, performing maintenance on some sort of schedule based on the running hours of the equipment or the distance traveled by haul trucks, for example, or the number of cycles completed and that sort of thing. But we need a strategy to do this properly, so we've got the right balance of this condition monitoring or condition-based maintenance, interval-based maintenance, and run-to-failure maintenance, where we have accepted that some equipment will fail and we're okay with that. But how do we set that up properly? It's very easy to just run off, buy a vibration system, get people trained, and start taking vibration readings. You will have some success, but won't be all that it could be. So this is why we need to go through the reliability strategy part of the plan. First, we're going to just make sure everything's organized. We know what the assets are in our plant. We have an up-to-date asset register. Okay. Then what we suggest is that you, at this point, go through an asset criticality ranking process. Now, I'll talk a bit more about that in a moment, but if you understand the criticality of your equipment, you can make all of these decisions and justify anything that you're doing and a lot more. And as part of that, you will then decide how detailed the reliability analysis has to be. So we do need to understand our failure modes so that we can correctly choose the condition monitoring technologies. We need to know quite a bit about the equipment. It's just that we may not choose to perform the classical, very detailed RCM or failure modes effects analysis on every single asset. We may just do that on 10 to 20% of the most critical assets. And maybe we will also do a reliability study. There's a lot I could say on that topic. I think it's a good thing to do, remembering that the failures are random, and I'll talk more about that in a moment. Okay, so if we go through this process, we will have a better maintenance program. We will perform maintenance when it's really warranted. But you can't improve reliability with maintenance alone. We need to get ahead of the curve and seek to improve the condition, and thus we'll do less maintenance and we'll find fewer problems. So that's what we're going to talk about in this section. I'm going to talk about much more detail in a moment. That number one, we have to say the design and procurement process is probably letting us down right now. It's allowing equipment with reliability issues into the plant. We've got to stop that. We've got to look at spares management, not only from a cost reduction standpoint and a way of improving our work practices, but as a way of improving reliability as well. Same with planning and scheduling. We can save an awful lot of money if we plan and schedule properly, but we can also improve our maintenance practices and achieve higher reliability if we perform planning and scheduling correctly. And as part of that, when we do work on the machines, when we're aligning them, when we're installing bearings, when we're balancing them and tightening the bolts and so on, we do that in a precision way. We do that so that we do achieve good reliability. And we have to look at how we're operating the equipment. There's a great source of reliability problems generated just because of the way we operate the equipment. And then we look at the way we perform our ongoing maintenance, cleaning, lubricating, adjusting, and preserving the function, which is the key goal of the maintenance role. Everything that we've discussed so far is all, or may seem to be, technical in nature. Doing some analysis, doing some vibration, preventive maintenance tasks, etc., etc. But there is a key component missing, and you guessed it, it lives over here. If you don't develop a reliability culture, you will achieve some benefit, but not all that you could achieve. So step one is to make sure you've got good leadership that has bought into this program and is willing to say so, plus a steering committee. We need a strategy and a vision for what we're going to try and achieve. But we're going to have a real focus on people, understanding human nature and why certain mistakes are made, but understanding change management. How can we get all of the people involved in all of these areas to change their practices so that we have better reliability? And a big part of that is training. Training to improve the knowledge and skills, and training to achieve buy-in, so that people aren't just doing a better job because they've been told to or because they've been trained to. It's doing a better job because they want to. And finally, we have to look at the continuous improvement. This is not a 6-month project or a 12-month project. You will achieve great results in 6 months and 12 months, but this is an ongoing. This is the future of the organization. Safety wasn't sort of fixed in 6 months and then just forgotten because it's all better. It's an ongoing process of education and awareness and so on. And improving reliability has to be the same. But we need root cause failure analysis. We need KPIs to monitor our progress and communicate the benefits and so on. So this is the roadmap to reliability, and it is a holistic approach. It is trying to take everything into account. It's not just a little focused program of buying a vibration analyzer or buying a shaft alignment system. It's taking everything into account and then rolling it out in an organized way. So that's the summary. Let's have a look at each one of these little building blocks in a bit more detail. Just a bit more detail. Okay, so leadership. We do need that strong leadership and sustained leadership. So by far, the most successful reliability improvement programs are the ones where senior management says, yes, I can see that my goals and objectives are being improved, are being achieved by improving reliability. So they're worried about safety and uptime and capacity and costs and risk and insurance and shareholders and regulators. Well, reliability ticks all of those boxes, and you just have to put it in the right language to them so they understand it, and then so they support it. And when they support it, then everyone in the organization knows that they need to be part of it. But you need some sort of steering committee as well, some sort of group of people who ideally represent quality and safety as well as maintenance and operations, who are there to head up the charge. But it's not just up to them to do it. You can't just have a reliability group and everyone throws the problems over the fence to the reliability group and says, hey, you guys fix this. Reliability is everyone's issue, just the same way safety is. There might be a champion, one person who's seen as the real driving force, but it is critical that you're able to have a bigger group that all buy into it, and if that champion gets promoted or poached by another company, then the program just rolls on. Okay, so now that we have that foundational piece in place, next we need the strategy and the vision. Now, I would like to think that this roadmap to reliability could play a key part of your strategy. As you have possibly seen already, but as we go through this presentation, there's nothing unique or proprietary from our point of view. You can adopt all of these elements yourself. But anyway, first we need some sort of vision statement. These statements can just serve to remind people constantly that reliability is important. You can say whatever you like, of course, but a suggestion would be, we will eliminate defects, base maintenance decisions on condition, and maximize safety through reliability improvement. Okay, but just something that people see as a reminder, yep, reliability is important, reliability is important. Second thing is that we need to perform some sort of benchmarking. There are a number of reasons for this. One of the key reasons is that as time goes on and reliability improves, you will probably have pressure from above to even reduce the costs of the reliability improvement initiative. If you've got condition monitoring people, you've got people with training to do the lubrication, and you got a lubrication storeroom and all these things going on, people might say, hey, I can save some money by getting rid of this because we don't have much of a reliability problem. Well, if you benchmark and look at these key metrics and say, okay, this is where we are now, this is how much downtime, these are our maintenance costs, this is, etc., how we're going according to our maintenance plan, and so on. If you can say, well, this is where we are today, and you do that as early as possible, then as you improve over time, you can always compare back to that time and say, well, if you pull the plug on reliability, we are headed back there, and I guarantee you it's been done again and again and again. You will head back there, you will. But as part of this, it's also helpful to compare yourself to best practice. If you're in the chemical industry or the paper industry or something like that, then you should be able to find benchmarking information out there from SMRP, or you can contact us, Aberdeen Research, and you can compare yourself to others in your industry. But if nothing else, even just compare yourself to the design spec for the plant, what the plant was supposed to be able to achieve, or what you have achieved on your best day in the past. Either way, you need to sort of put a flag in the ground and say, well, this is our starting point, we want to improve on this, and these are our opportunities, these are our gaps to what we think we can achieve. And as part of all of this, we develop key performance indicators. We use those to measure the progress, not to use as a stick to beat people with, hey, you're not achieving these results. Don't use them in such a way that people feel some artificial pressure to achieve those results, which can be counterproductive to the actual reliability improvement initiative and the goals of the plant. So one of the keys is to measure what you want to improve and make sure that people understand that KPIs are there to identify where there are problems, not in terms of you as a manager, let's say, but if we're not achieving our stated goal of uptime or OEE or something like that, well, don't try and fake the results so that you do appear to be better. Use it as a learning experience and say, okay, well, we need to improve and this is an opportunity. Okay, so now we need to talk about the people in the organization, because this is where the fight will be won or lost. Everyone must believe in reliability improvement, just as everyone hopefully believes in safety. They realize that their own safety, the safety of their co-workers, and the future viability of the plant relies on it being safe. Well, the same is all true for reliability, and people have to realize that, and people have to realize that there are many other benefits to working in a reliable plant. But as part of this, it's important that everyone understand how they can contribute and participate in the process. If they feel like it's just something that's being done to them, or that there's some special group being set up to tackle this, they'll say, it's just another one of those programs and doesn't involve me. Now, people, you achieve buy-in when people can contribute and they feel rewarded for the suggestions they make and the changes they make. We also have to reduce or remove the fear. If a person, for example, has a job to repair equipment that's failed, and you're saying, well, we want to have fewer failures, they might say, well, that's my job, isn't it? So you've got to be able to answer, what's in it for me. And there are good answers to all those sorts of questions. But as part of this, we have to understand human error, why these problems come up in the first place, why jobs aren't done correctly, why mistakes are made, etc. And also human nature. We can talk about human psychology and the psychology of reliability. Just we can sometimes make the mistake of treating people like robots. I ask you to do a job this way and therefore you will do it that way. People are obviously far more complex than that, and we have to make sure that people do actually change because they want to change. So, a part of the solution, it's a big part, but a part of the solution is how we communicate the good news and also the bad news. If something doesn't quite work out the way we want, don't hide it, don't sweep it under the carpet, just say, well, okay, we tried this, it didn't work, but this is why and what we're going to do about it. The more you can give people credit and ownership of the achievements, the more buy-in you will get. The more the people standing in the corner with their arms crossed, not buying into it, will get involved because they'll say, hey, I want a bit of credit for what's going on and I can see it's working for other people. So we have to continue to sell the benefits, give people recognition for the improvements that they make, and so on. So, how do we gather the skills and the knowledge and the buy-in? Well, it's through training. However you do the training. Okay, we're a training company and we have iLearn Reliability, but I'll say, there are other sources of reliability training, and you can develop things yourself. You can create lunch and learns and toolbox talks and all these sorts of things. So, this isn't just a sales pitch. Training is absolutely essential. There is no doubt that you must look at training as a key component of this whole strategy. You need to create awareness and buy-in through training, by demystifying what all these things are about, by explaining the benefits of it, so on and so on. But obviously you also need the knowledge and skills. Now, I would argue that most of what I'm talking about today, if not everything, is common sense, and it's not rocket science. You don't have to be, some PhD in something to understand how to align a machine properly or how to, improve your lubrication contamination issues and things like that. But you do need training to develop that knowledge and the skills, the specific skills on how do you align a machine properly, to use that example again. So training is important, but everyone has to be trained. A big mistake I see is that, for example, a few people in the reliability group will go off and get some training somewhere, or they go to conferences and they come back and they think, wow, right at this point in time, I have a certain amount of knowledge, which is fantastic, and I'm glad I have it. And right at that point in time, they feel some enthusiasm for it and everything else. But then they're facing an organization that doesn't get it, that hasn't been on that training, that doesn't know what you're talking about. So you got these little pockets of knowledge, just a few people knowing this and a few people knowing that. You got some guys who understand vibration analysis and some people who understand shaft alignment or whatever it is. Everyone has to understand. I'm going to say everything. Obviously there's some limitations to that, but clearly not at the same level. And that's the key to all of this. Training needs to be layered so that at one end you can have toolbox talks where people just get an introduction to these various topics. They understand what their role is. They understand what the benefits are. They understand, just demystify this whole question of why it matters if there's water in the oil or if the machine isn't aligned properly and everything else. Just demystify it. People feel involved. People feel like you're sharing with them and taking the time and going to the effort to get them involved. And of course, at the other end of the spectrum, we can have detailed training on vibration and root cause failure analysis or whatever. But please don't make the mistake of just training some people and not others. And recognize that with staff turnovers, there's new people to train when they come on board, and people forget things. You can go through some training. Think about it yourself. Think of some training you went on 6 months ago or 12 months ago. Can you remember everything they taught you? Would some refresher training help? Anyway, put that into your training plans. Okay, so now we're going to deal with some, let's call it, technical issues. Number one, we do have to understand our assets. We do need an up-to-date asset register or master equipment list that is accurate and that is kept accurate. Now, this is where we differ in certain ways to companies that would recommend a full detailed classical RCM. We would argue that if at this stage, to get the program rolling, to get some real action going so that you can prioritize what you do, what we need to do is determine what the criticality is of each of our assets. And we can then use that information to decide where we might perform a more detailed RCM or FMEA. We can then use that information to look at our spares management and look at how we prioritize work orders and where we can justify condition monitoring and so on. Developing the asset criticality ranking is more detailed than just saying, okay, this asset has moderate criticality, that asset has extreme criticality or whatever. We don't have time to discuss this in detail now, but we do have other presentations on this. The idea is to break the consequences of failure into multiple categories, whether it's quality and safety and impact on production, impact to the environment, impact on people, and impact on production and the equipment itself. So we can look for an individual asset in your plant. You're going to consider, yes, there are lots of failure modes and potential consequences, but you just need to step back and say, okay, what are we concerned about with a particular piece of equipment? And if we can go through and assign the consequence in each of these areas, and you decide on your own, then and record this information, then you've got a good record of how those decisions were made and why. But we need to take one extra step and say, okay, these are the consequences, but how likely are these consequences? Is it rare that this equipment fails, or is it quite common for it to fail? So that combination of all of this consequence information, the combination of all of this and the likelihood of failure gives us the criticality ranking. Now there's much more we could talk about, but I just want to give you an idea of that. And then with that information, there's all sorts of decisions we can make. And we may break that information up into just purely reliability questions versus safety and so on to make certain decisions, but basically that asset criticality ranking is very important in all of this. So, now that we understand criticality and we can therefore justify where we do detailed analysis, we can justify where we do condition monitoring and so on, we now need to look at the failure modes of our equipment so that we can devise our maintenance strategy. And again, yes, we could do a very detailed RCM analysis, but I think it's possible to do it without such rigor. Rigor's great, but it takes a lot of time and potentially takes a lot of money and experience and consulting help and so on. And there have been a lot of these programs that have started and never really achieved any results. So this is, I'd like to think, a more practical approach. But the reason I have this particular graph on the screen is because you can't make the decisions you're required to make unless you understand some basic principles about failure modes. And that is that the majority of your equipment, particularly rotating machinery, has this failure pattern. And what that means is that if we took a whole lot of your motors, pumps, fans, compressors and so on, and looked at, and even a class, even just your motors, and said, when do they fail? When do the bearings fail? Do they all last 8 months and then begin to fail, and within another 4 months they've all failed? If that was the case, we would be having age-related failures, where we can predict based on operating hours when the equipment's likely to fail. But that's not our reality. Our reality is what we call random failures, in which case there is no higher probability of failure today as there is that day or that day or that day. The only thing we do know is that more than likely, when you first start that machine after it's been aligned and bearings have been installed or whatever, there's a much higher likelihood it'll fail then. And over time, if it doesn't fail, then the probability of failure drops down, and then we're into this random section. So this tells you, on the one hand, you need to do a really good job working on the equipment. But on the other hand, the best thing you can do is leave the equipment alone. Once you do some maintenance on it, if you replace bearings or seals or whatever, there's a pretty high likelihood that it'll fail. Now, you may have better maintenance practices, in which case the infant mortality area is not as big of an issue, but it's still random. What random means is that interval-based maintenance doesn't work. So you need to understand all of this so that you can then make these decisions. These are the 7 steps in a reliability-centered maintenance program. But as I mentioned earlier, we can go through a more streamlined approach to consider these issues, because from these issues I'm able to design my condition monitoring program and interval-based maintenance program. Now, we don't have time to go through this in a whole lot of detail, but basically the first thing you have to do is say, well, what are the consequences of failure of a particular asset? And if we go through that process and say, you know what, we don't have any of these consequences, then what we're saying is we don't care if it fails. Okay, we don't want it to fail. If we could avoid the failure, we would. But how much money are we going to spend to avoid it failing if the consequences are so minor? But we, of course, have other situations where, oops, we don't want it to fail. So then we say, well, could we use condition monitoring? That's our go-to option. And if we can, we'll do it. If we can't, then we'll say, okay, can we use an interval-based approach, replacing the belts after X number of months? And if so, okay, we'll do that. If we can't, then we're in a bit of a pickle, because we can't monitor it, we can't prevent it, we don't want it to fail, but it will fail. So we either redesign it or we just accept the risk. Okay, so now that we've been through that, we can consider doing a more detailed reliability study, collecting all this information, doing viable analysis and all of that. Now, I just believe that your time is best spent focusing on improving reliability, not measuring it. Measure it all you like, but you've got random failures, and it can take a long time before you can really understand the history of particular types of equipment. So, go ahead and record the information. Look, there's so much we could talk about on this particular topic, but my bottom line is, do it by all means, but don't make that your focus. Make your focus improving reliability. And you can focus on all these common approaches that I'm about to talk about. So, as I mentioned, our starting point is, hey, if there's no great consequence of failure, well, we'll just let it fail. It's not worth our time and resources to perform some routine maintenance action to prevent it, or to perform condition monitoring to detect the onset of failure. Every measurement you take and every measurement you analyze and everything else costs time and money. And unless you happen to be lucky and have oodles of both, then it's not necessary to do this. But it is necessary to perform condition monitoring, and this should represent, for most industries, about 80% of your assets. The decisions should come from, based on condition. Now, if you haven't seen this before, this is sort of a PF curve, but the idea is that your equipment runs for a certain period of time with good condition. Good conditions up here, it's all good. But at some point, it's going to begin to fail. The bearings are going to begin to fail. Why? Could be a lot of different reasons. It could be a lubrication issue, an alignment issue, a balance issue, an installation issue, all sorts of issues. But we want to know that that's happening, because our risk is going up when this happens. So as our condition degrades, we can use these technologies to detect that there's that degradation and monitor it. Now, of course, we just keep monitoring, it will fail. Bang. It'll get to a functional failure where it's unable to do its job, and it may fail catastrophically. But we need to be monitoring it during this time, because the earlier we detect the problem, which could be through vibration, oil analysis, ultrasound, whatever, the earlier we detect it, we are now in the driver's seat. And I'll mention a bit more about this in just a moment, but puts us in the driver's seat. Our risk of failure and downtime and safety issues is low. The costs associated with dealing with this problem are as low as they're going to be. And you might say, oh, but I'm going to replace the bearing right here, 5 minutes before it would have failed. Man, you're creating all kinds of risks and safety issues and cost issues. You're better doing something as early as possible, doing it in an orderly manner, less stress, less rush, haste, and safer, lower costs. So the longer you leave it, the risk goes up, the costs go up because you have less planning time. What we really want to do, of course, is live here. And that's what all this is about. Yes, it's great to have condition monitoring, but what we want is to live in this sort of defect-free, good condition, trouble-free operation zone. That's what we want. Very briefly, the telltale signs, yes, you can measure vibration, the sound, temperature, the voltage, current and impedance from electric motors and other things. The chemistry of the oil, deposits in the oil, particles, wear particles and so on, and contamination, and the performance of the equipment. And as part of all of this, and I should have put somewhere there, the visual inspections as well. They are all condition monitoring. Whether you're going out there just to inspect a bearing or the tires on a haul truck or whatever, or whether you're actually measuring vibration with a fancy instrument, it's all condition monitoring, because we are going to use that condition information to make our decision. Now, one little detail I'd like to just pop in here with our condition monitoring program. If we understand criticality, then we can make the decisions about which assets should be tested. And we can also decide if we will overlap a little. We'll use multiple technologies on a particular piece of equipment to increase our confidence in detecting the problem and confidence in getting the diagnosis right. But we're going to use the PF interval, the time between potential failure, when we can detect the problem, to functional failure. We're going to use some knowledge about that to determine how frequently we perform the tests. We may need a continuous monitoring system because it can go from healthy to completely catastrophically failed in a short period of time, or we might use a handheld vibration system which we use every 30 days. But we need to understand something of the failure modes so that we understand, okay, well, vibration can detect that, oil analysis can detect that, infrared can detect that. And we also need to assess our own capabilities. Do we have the internal people who can perform these measurements and tests, or do we need to use outside contractors as well? So that's all important decisions. We also need to remember we need something called a failure finding task. Imagine that Unit A here was running, and the vibration analyst walks up and does a test and says, yep, it's good, but maybe a problem's developing. And it's all good, but no one's looking at Unit B that's in standby mode. And the assumption is that if we need to shut down Unit A, Unit B will start up and give us lots of time of trouble-free operation while we deal with whatever issue we have with Unit A. But Unit B sitting there might be vibrating and damaging the bearings. We might have some oil in the lubricant. We might find that when we turn on Unit B, it fails quite quickly. And that's one type of hidden failure. So as part of our condition monitoring program, we also need to perform tests to make sure that those sorts of faults can be detected. Okay, so then we have interval-based maintenance, often called preventive maintenance, but in some texts preventive has condition monitoring as a subset. So interval-based maintenance means I'm going to perform a restoration process or a replacement process on a set interval, which may be based on calendar days, running hours, number of cycles of production, distance traveled by a truck, whatever. But first we should say, can we use condition monitoring, in a cost-effective way? And is this an age-related failure mode? Age-related failure modes mean that the more we operate it, the higher the likelihood of failure is, because something is wearing out, for example. So that might only be 10% of your equipment, could even be less. So now we're going to talk about all those little blocks that were on the right hand side of the roadmap to reliability. And what this is all about really is defect elimination. It's looking at all the reasons, all those root causes why our electrical and mechanical equipment fails. And rather than waiting for failure and doing root cause failure analysis, why don't we think about all the problems that every plant has and do something about them? Just be proactive about it. If you know that a problem could occur, let's try and avoid it. So step one is in the design process. Is the design process can often be very engineering oriented. Right, I need a pump to perform a certain function and it needs to sit this high off the ground, and etc. So you go through that process, and then the procurement department says, okay, well, I just need a pump that meets these minimum requirements. But does the design process look at maintainability, reliability, and operability? Are the maintenance people and condition monitoring people and operations people involved with the design process and selection criteria? Now, it's not to say that every single little decision has to be bounced off people in these departments, but it just seems bizarre to me that decisions like this would be made when there are people in the organization that have had experience with that type of equipment, possibly that vendor, that process before. They have real life practical experience and they know about the maintainability issues, etc. They should assist in the design process so that what we design and specify will meet our requirements. Is the motor rated properly? It's amazing how often motors are rated well over what they need to be, and it's not good for the motor. Is it energy efficient? Is the pump rated properly? Or was some original specs put in place, but they've been inflated to build in extra sort of protection, but in actual fact we have a less reliable pump as a result. We have to be able to operate that pump at its best efficiency point. So that takes us to procurement. The procurement department generally is just there to say, well, okay, here are the specifications I've been given. What's the cheapest one I can buy? They're there to save money and they're motivated that way. But what we want is to purchase equipment that gives us the lowest life cycle costs. All of these costs, it's not all about the purchase price, but about the maintenance cost, the downtime cost, the operating cost, etc., etc., etc. What's that all costing us? So we need to go beyond the purchase cost. But the procurement department is probably not skilled enough to make these assessments. And that's why the design process in the first place has to set the bar higher. Now, what do I mean by that? The easiest analogy is that we have these, so we want to go and buy a motor coupled to a pump on a skid, let's say, and we have a number of options presented to us. Now, those options, because of the specifications, the way it was manufactured, where it's come from, etc., they will have different prices. So this is the most expensive, this is the least expensive. But it will also have certain defects, let's say. Its quality, the defects can be sort of hidden from us unless we specifically test for them, and I'll talk about that later. But anyway, what we need to do is set the bar higher. So rather than the decision just being made on cost, so all of those meet the requirements from the design department, so therefore I choose the cheapest one that's going to give us all sorts of grief. There are all the defects inside. What we need to do is say no, life cycle costs. So the design department says no, only these two meet our requirements. These two do not. And because these two are equal from a reliability point of view, the procurement department just says, oh, well, this is the cheaper, we buy that. And what we know is that the asset that comes into our plant is fit for purpose. Because we really need to think about, where it's coming from, how it's been stored, who the vendor is, and these sorts of things. We also need to think about counterfeit parts, because if our whole sole focus is on cutting costs, it's quite likely that you'll end up with counterfeit bearings, counterfeit oil filters, counterfeit, you name it. And all of this applies to the contractors that we have come on site and outside services, motor rewinds, balance jobs, etc. We don't want to have jobs done that leads to failure. We want the balance jobs to be done properly, but if you don't specify how good the balance job has to be, well, you won't get a very good balance. It'll seem okay, it'll seem better than it was, but it won't be precision. And the same goes with transportation. Hey, how is the equipment being transported? Are the bearings locked down? Could there be vibration and causing false Brinelling? Could there be corrosion problems and so on? Now we need to look at spares management. There's really two sides to this. On the one hand, if we understand criticality, we can decide what spares we really need to keep in inventory. We can save an awful lot of money just in this area, because we often keep lots and lots of spares that we may never use, that may be redundant, and we're tying up an awful lot of money. These holding costs can be very high. The overall maintenance budget can be tied up with what we have in inventory, and it's just not necessary. So there's a lot that could be said on that topic, but also we have to look at the possibility that when we have the bearings and motors and pumps on our shelves, we're damaging them because of vibration, dust and contamination and humidity and just the aging of rubber components and so on. Our database may say that motor is in store, so when we go to use it, we're stuck using something that's probably going to give us problems pretty quickly, same as these bearings. And that's what is probably happening in your plant right now. And that's, of course, assuming that everything that's on the shelves is in the database and vice versa. So, now that we've got our spares being managed properly, we need to look at the planning process. Again, the planning process really has two aspects. One is just from a cost basis. It is far more cost effective and has great implications on safety and other areas if we can plan properly. So if we've got, rather than just a crew of maintenance people, we take one of those people out and make that person the planner, then jobs are performed far more effectively, the costs are reduced, there's far less waste and so on. The aim is to have the person with the right skills, using the right tools, with the right parts, with clear instructions and all that sort of stuff, doing the job. So if we use condition monitoring and we have proper planning, it'll all be good. If we have poor planning and we don't have a good warning of problems, then hopefully we'll get the job done, but it means we have to keep many more parts in inventory or spend a lot of money getting urgent parts in. Look, there's a lot we could talk about there. What we aim for is determining there's a problem early, and in an organized, studious way, we're going to perform that, the plan and then the job. No risk of failure, much lower costs, it's all good. Something just to consider is that we can use operator-driven reliability as well. So operators can potentially perform some cleaning tasks, some minor maintenance tasks. They can perform condition monitoring tasks, simple condition monitoring tasks as well. It really reduces the workload. It improves the information you get back from the about the plant. It makes operators more aware of what's going on with the equipment. It's many benefits to this. And then, of course, along with planning, we have the scheduling process, but the same thing. We have to make sure that we got the job done properly. We want to plan in advance. We want to make sure that the jobs are being planned and scheduled correctly. So we need some feedback to make sure that the jobs were actually done properly, that the plan was actually effective and everything else. So scheduling is very important. So let's look at precision skills. So now the job's actually going to be done. Well, it's got to be done properly. We need to do these jobs in a precision way. Alignment is one of the keys for sure. Misalignment, the forces associated with misalignment destroy bearings, couplings, seals, shafts, etc. You can't perform straight edge alignment. There is no way you can get anywhere close to precision alignment with straight edge. You can with dial indicator alignment, but most people don't. And you can with laser alignment, but a lot of people don't. It's better with laser alignment. Straight edge, it's just, no, you shouldn't do it. Any misalignment creates a lot of force and load on the bearings and couplings and so on. This is, okay, these are exaggerated, these animations, but it just shows what it's trying to do. When you bolt those feet down, all those forces are being transmitted through the bearings and seals and so on, and it causes damage. We can't talk about this in any detail, but what the x-axis here is the amount of angular misalignment. So imagine there's a sort of the two couplings aren't flush, there's a bit of a gap. But this is 5/60ths of a degree, and it's reducing the life to 50%. So this is a research study that was performed. So it's important to precision align. But I want to say something tiny bit controversial perhaps. But just because you've purchased laser alignment equipment does not mean you have precision alignment. Don't think you've ticked that box. So often people buy it, it's just sort of, hey guys, here's something new and shiny to use, go and use it. And it's often not used or not used properly. And just because the vibration analysts aren't constantly warning you about misalignment, that does not mean that machines are properly aligned. Unfortunately, machines can be misaligned and the vibration doesn't really change, or it's not recognized, but sometimes it just doesn't change. Doesn't mean it's not doing damage, it's just not detected. So, and the same goes for belts, making sure the pulleys or sheaves are in line, no offset, no angle and so on, and the tension is correct. And we have to look at soft foot. A lot of people don't know what soft foot is, and that includes the people doing the alignment job. What we need is for all 4 feet to sit flat on the base before we tighten the bolts. And so that when we tighten the bolts, we're not stressing the case of the machine. But if we've got this situation where a foot is bent, very, very, very common. Or we've got this situation, and it may not be bent, it may be just offset, it may be very rough castings underneath. But if you look at this situation, the base that we're mounting the machine on may not be flat. And that's soft foot, and that causes a lot of damage to the machine as well. Then we have to look at how we fasten. When we are tightening the bolts, are we doing it in the correct sequence, to the correct torque? Are we using the right sorts of bolts and washers and so on in the correct sequence? It's important for electrical connections and mechanical as well. Okay, balancing. Now, balancing is one of those things that most people are aware of, but unfortunately, the person doing the balance job simply sees high vibration and balances it until the vibration is acceptable again, and off you go. Okay, that's fine, but number one, you should be balancing to G 1.0 or better. Make sure the people doing it actually understand what G 1.0 means. So aim for that level of balance quality and make sure that the person can do it, that has the right tools and can get to that. The other issue is too that often what happens is the machine vibration gets worse and worse and worse and worse until it's like, okay, that vibration's bad enough that we better fix it. I mean, it's really vibrating a lot. The trouble is that all that time between the time it was precision balanced and the time you do the job, the bearings are taking it in the shorts. The machine is vibrating and it is reducing the life of the machine. So the bottom line is we need to take the opportunity to improve the balance state when we can. All of these have a cost-benefit analysis. Do you balance it every week just in case? Obviously not, but you need to strike a balance, because as that dirt builds up on the fans, it builds up on the blades, it builds up unevenly, and when it operates, not only does this move up and down, but it rocks from side to side if it's overhung like this, and that just damages the structure, the bearings, the motor. It's just not good. And I'm not just talking about when the vibration levels are really high, I'm talking about even when they're moderate. Okay, we have to make sure we install the bearing properly too. We don't want obvious issues like breaking away pieces of metal and gouging the raceways, but even if there's slight a misalignment, a slight cocked bearing. The inner race is just on an angle. Now this is exaggerated, but this is what's happening with every rotation. There's additional pressure and forces being placed on the raceways and the rolling elements. Okay. Now, there's other areas we could discuss in terms of precision maintenance and the skills required, but now we're going to operate the machine. We have to make sure we operate the equipment in a consistent way that achieves let's just say the lowest life cycle costs. We obviously the machine has a job to do from a production standpoint, but we need to do that so that we extend the life of the equipment, or we don't reduce it. So we're going to operate it with precision, and in certain industries this can represent the biggest source of reliability problems. Yes, bigger than maintenance. A lot of times machines fail just because of the way they're being operated. So you need standard operating procedures. You need to operate consistently between shifts. You need to operate pumps at their best efficiency point, and so on. And if you don't, then this is what happens. We get recirculation, cavitation, the bearings, the seals potentially, the impeller and shaft are all damaged as a result. So we need to operate the pump properly. So, now a moment ago I talked about the skills involved with the repair process or the restoration process. Now there's the ongoing maintenance to maintain its function. We're going to lubricate it, clean it, make adjustments, and do everything we can to ensure the longevity of the equipment. Lubrication is one of the keys for sure. We have to give it the right lubrication and it's not contaminated. There is just a 1 micron gap between the surfaces of a bearing or gears, gear teeth. 1 micron is 1/millionth of a meter, which is about a yard. So it's a very, very small gap. That lubricant is doing an amazing job keeping those surfaces apart, stopping the roughness that if you looked at it at a microscopic level exists, keeping those surfaces apart, doing an important job. So if it's contaminated, or it's the wrong lubricant, or the lubricant additive pack is depleted or whatever, all of that reduces the life of your machines. So we've got to keep it cool, we've got to keep it clean of all sorts of contaminants, and we need it to have the right specification. Obviously this is an extreme case. Someone's got just loves their grease gun. Maybe they think it's their gym workout or something. In the extreme, greasing a bearing, you can get all sorts of bad results, but too little grease and too much grease damage bearings. So on contamination, we need to look at the lubricant properties themselves. So a lubricant has an additive pack and has viscosity, but you add water and you affect that. And there's other contaminants that affect the lubricant properties, and then over time also they can be depleted. We need to monitor for that. The contamination, particularly water for example, can corrode the surfaces of the gears and the bearings, and then there's the issue with particles as well. So in this particular case, imagine you've got a standby machine and there's a bit of water in the oil. The water can pool up around the rollers and cause corrosion, and then when you turn on that machine it'll fail quite quickly. But in this case there's probably been enough water that's come out of solution and caused this damage. The amount of water that can cause damage is so low there's no way you can see it. You can't hold up a tube of oil and see the water. By the time you can see it, there's gross amounts of damage being done. We need to consider particles as well. Now these aren't, in my animation it looks like a great big boulder sitting in there. This might be a particle of 3, 4, 5 microns in size, very small, that's enough to get between the rolling element and the bearing, or between the teeth of the gears, and it does damage. And even though that's a small particle and therefore creates a small bit of damage, the damage spreads. We start with a tiny little point and it gets worse and worse and worse and ends up obviously causing serious problems. This study, again, love to have more time to discuss all of these, but a study was done where they used progressively better filters, starting at 40 microns, then 25 microns, 10 microns, 6, and then finally 3 micron filtration. And they compared that to the life of gears. And so, as they improved the filtration, they achieved improved life. But it was only when they dropped down to 3 micron filtration where they really got the benefits. So that's what you need to be aiming for as well. Again, you can do root cause failure analysis and all this sort of stuff. The fact is that if you're not dealing with the sources of contamination and performing this kind of filtration, this will be damaging your machines. It will be damaging your machines, whether you know it or not. So, we've identified, or I've just identified, a number of common sources of root causes for failures. And there's a lot more we could talk about. We could talk about it in more detail, but it's not enough to just turn around and say, okay, well, we'll change our design process, we'll improve the way we do procurement, we'll make all these changes. You need a way to check that it's actually being done properly. So one way, very important, is acceptance testing, and it's not very commonly used. So it's okay to specify that a pump meets certain requirements, but you should, as part of the purchase agreement, say, basically, if it does not meet these standards, it does not get into the plant, and these are the tests we're going to perform. Those tests might include electrical tests, voltage, current, etc., on the motor. It would include vibration readings, and say, well, the vibration should be below this level at these individual frequencies, and this is how it should be tested. There's no reason why the vibration should be higher, and so there's no reason why a vendor shouldn't agree to these terms. Now, they might put up a bit of a fight, but this has been done in a large number of plants in different sorts of industries in different parts of the world. It can be done, and it should be, because you would be amazed how many times you've purchased equipment and it already had faults, that it already had problems. It should have been rejected right at the start. The best case scenario for you is that you run it and within the warranty period something goes wrong and you can convince them that it was under their warranty, that it wasn't you, that it was their problem, and then you can go to all the hassle of having to replace it and whatnot. What a hassle. And that's if you're lucky enough to detect it and prove that it was that they were the reason for the problem. In a lot of other cases you just adopt those problems and it's not good. And we also need to use these QA, QC, quality assurance, quality control methods, basically condition monitoring, to verify that the fault diagnoses were correct, but also that the machine has been set up correctly. So you report that there's a vibration problem because the bearings are failing, the bearings are replaced. You then inspect the bearings to make sure, just how severe the problem was. And you test the machine afterwards to make sure that no other problems have been introduced and that whatever vibration pattern you saw has gone away. So it's just an important part. But just for a moment we need to dwell on condition monitoring, because condition monitoring in too many plants is used as a sort of like a troubleshooting tool. It's sort of like old Joe who used to walk around with the screwdriver and listen to bearings. Oops, we've got a problem here. Well, that was great, Joe. That was great, but we'd like, more warning of the problems. So you buy a vibration analyzer, and you might find out weeks and months before, if you use it properly, that there's a problem. And that's good, but you're still reacting to problems that shouldn't exist. We need to look for ways to reduce the likelihood of those problems occurring. So we use our condition monitoring to improve reliability. We can use it in acceptance testing as I've just described, but for example, if we are checking the lubricant and we see that there's something wrong with the properties or there's contamination, we do something about it. We look for misalignment and unbalance and looseness and resonance, and rather than waiting for the problems to become severe where we've sort of got our hands tied and we have to deal with it, we take the opportunity, we have to consider issues with downtime and labour and so on, but we take the opportunities earlier rather than later to correct the misalignment or the unbalance or the resonance problem, so that we don't reduce the life of the equipment. We can also look at the performance and see how it's being operated. Is there cavitation or is it just out of spec? So that way condition monitoring is used to improve reliability, just not measure the results of poor reliability. Okay, we're at the last stage now. We've got all of these pieces in place, but this isn't a project where we're going to make all these changes and then walk away, dust our hands and say, great, we're done, I've got this all in place. We need to be developing this over a period of time. We need ongoing training and so on, but we need a way to evaluate how we're going and improve what we're doing. Root cause failure analysis is an important part. We're going to, if there is a bearing failure, there will be bearing failures, so we're going to see, well, why did it occur? Is it something we could have avoided? Could we have used a different installation process? Is it the right bearing for the application? Is the lubricant right? These sorts of things. We're going to look at those KPIs that we set up at the beginning. We're going to collect the data and we're going to watch those KPIs. We're going to use those KPIs to keep people's awareness, just as you might have a sign at your gate saying, how many days it has been since the last, lost time incident. You could also have a trend somewhere of your OEE. Hey, this is how we're doing. We are improving. We're reducing our downtime. We're improving quality and throughput. That helps sell it to everyone, including people at the highest levels. And we just need to look at our strategy and say, okay, what more could we do? What else can we do? And so it is all part of a continuous improvement process to continue to educate, to continue to improve, to sell the benefits so that we don't have the rug pulled out from underneath us. And so that's our roadmap to reliability. We put together our maintenance strategy. We looked at defect elimination to root out all those sources of problems. We took care of all the human issues, which are really make or break issues. Having the leadership in place, having people buy into it, having people with the right knowledge and skills and attitude, and we can continuously improve the process as well. And that, to me, is a holistic approach to this. If you go through a process like this, you will have improved reliability, you will reduce the cost, you will have greater availability and uptime, but it will be sustainable, and that's the key. There are so many programs where people buy a bit of vibration equipment or whatever it is. They just do little bits here and there, and they all have their little benefits. But over the long term, these programs don't work. The vibration program falls aside, the lubrication program falls aside. I believe if you follow a process like that, it will be sustainable for the long haul. So, reliability represents a huge opportunity. A bunch of what I talked about is technical in nature, and you need the knowledge and skills and tools, but a lot of things don't need that much of an investment, I would say. You're not out to spend a lot of money to do a lot of these things. It's more what people do inside the organization and doing them properly. But we need that reliability culture. That is the difference between plants that have success and plants that don't. And if you do all of that, I truly believe you will enjoy the benefits of improved reliability. So thank you very much for viewing this presentation. I hope you found it useful. I know it's a little bit longer. We have much shorter versions on this topic. We have lots of other training that goes through each of those elements in more detail. So thank you for viewing this presentation. You can contact me if you have any questions, but we have lots of other presentations on our website, and if you're interested in training in this field of vibration or anything, there's our general email address. We have training centres in 50 countries around the world. We train people from, I think it's over 150 countries, so there's lots out there. But I Learn Reliability is the product that teaches everything in the roadmap to reliability and can help you make that a reality. Anyway, thank you very much for your time.